Okay, yeah. Okay, for this lecture, first we take a look about the Vitis programming and execution models. And I talk about OpenCL programming models. Since the code is written in OpenCL, so we need to know about the OpenCL programming models. And then we will take a Lab3, go through its codes, yeah, and let you know its functions. And Lab3 is a very you can think about it's a template. Lab3 itself doesn't teach you much about high-level synthesis. Okay, however, the code of the Lab3 give you a template that can be generally used for any of the application accelerations. Yeah. So if a given open source code, yeah, you can try to replace some of the Lab3 module with the kernel function and still use its interface or communication between the kernel and host programs. Yeah, and that will make the future open source code porting easier. Okay, so this the Vitis programming execution model. Actually, OpenCL is the same programming models. So we have two parts. One is the host program running on the CPU. Okay, and the kernel function running in FPGA. Okay, so on the host side, you have a host program. Before you do the application acceleration, the host application and accelerated function actually are integrated parts running in the host, and then you separate them. Okay, so then you need the infrastructure, a framework to support this application acceleration. So in the host side, you have the XRT and its API and OS drivers. On the FPGA side, you need to have a hardware components, including the DMA engine, global memory, and the XI interface. Okay, yeah, and you need to remember that the host side, the driver, and the hardware component, they have to one-to-one binding. Okay, so when you download a certain version of a Vitis tools, you have to make sure you are using the right, the correct hardware modules, because all the drivers is bind to the its corresponding hardware IP. Yeah, you cannot mess up the tool. If you mess up the tool, the system will not work. Okay, yeah. So then how does it work is the kernel function always work with the global memory. Yeah. So the process of the host program and the kernel function is first step, the host application program has to prepare data and put into the host memory. Okay, and then next step is program the kernel function and its DMA engine. Yeah, first you program the DMA engine to move the host memory data to its global memory, and then you program necessary the kernel arguments to start the kernel execution. When kernel start execute, it's only operate on the global memory. Okay, kernel function does not rewrite system memory, host memory. So you have to prepare every data and move to the global memory first. Okay. Remember, kernel function does not directly access the host memory. Okay. So So the kernel function work with the global memory, and its results also save in the global memory. And the DMA engine move the global memory data to the host memory, and then the rest of the host program will take over to get the result data from the host memory. Yeah. So in this working model, I think that this working model is very simple and easy to manage. Yeah. However, it has a lot of overhead. Okay. I think that the most overhead is coming from the latency introduced due to the data movement. Okay. Yeah. So when you decide to adopt application acceleration, you have to judge the kernel function, the accelerated function that save the time you save, whether that can compensate all the data movement latency introduced. Okay, so for whole application, okay, when we talk about application acceleration, we are talking about the application, the whole application running efficient, whether it's running more faster than running in a single processor. So you have to consider the whole thing as your evaluation standards. You cannot simply look at kernel function. When you look at a lot of papers, he says the kernel function speed 2 order, 100 times faster. But he doesn't mention the whole application, how much it is speed up. I remember a few years ago, Microsoft first adopted FPGA in its edge, in its data centers, doing the search. Basically, use the FPGA to do the search engine. In the paper, he claims it's a 2 order speed up, more than 100 times the speed up for the search engine part. However, the whole application only speed up 2 times. Yeah. So when we talk about application acceleration, I would like advise you have to consider the whole application. So we will spend a lot of time, not simply on the HLS code optimization. We also spend a lot of time look at how do you write your host code? How do you manage the data transfer? How do you do the host application program pipeline with the kernel function? Yeah, so that's very very critical. Yeah. Okay, and then later in next slide, I will talk about the Vitis development flow. And Vitis 2 provide a lot of utility for you to do the system level analysis. Yeah. So yeah, you have to change your mindset. Don't focus simply on the HLS kernel function speed up. Yeah, and oftentimes the system operation optimization give you much more benefits. Okay, let's talk about the OpenCL programming models. Okay, and we are using the OpenCL. Okay, that's not the only way to do the host programs. If you look at a lot of open source, actually people use a lot of XRT. Oh, okay. Directly, they don't use OpenCL. The reason why use OpenCL because a lot of existing application program is written in OpenCL. Yeah. So that's why we teach you OpenCL. Yeah, and you will see people directly use the API from the XRT. Yeah, use the XRT. However, they are still stick to the same programming models. Yeah. Okay. So here I'm going to talk about the OpenCL framework. In OpenCL, there's a so-called platform. Okay. So a platform including the host and the OpenCL device. Okay. This is the platform. And for OpenCL device, in the OpenCL, the device it's original invented for GPU acceleration. Yeah. And however, the device could be CPU, GPU, DSP, or FPGA. So the OpenCL framework that when you write the host program, they try to make to hide the underlying computing device. So you can use the same host program as long as you are writing using the OpenCL framework. And the system, they will identify the device, switch to different type of device, and still the host program can still run. Okay, so you can use the GPU or use the FPGA or any other kind of accelerator device. As long as it stick to OpenCL, then the host program can run, yeah, without considering the underlying device. Yeah. So for each device, you have a compute unit. Okay, for each compute unit, you have the PE, processing element. Okay, so remember the OpenCL platform, including the OpenCL device. Each device, it has a compute unit. Under each compute unit, you have processing unit. You have to know the relationship because the memory model will be different. Yeah. For execution model, so for the execution model, basically you have a host program and the kernel part. Okay, and okay, and then there's a context. In here, we have to remember because all the OpenCL code tied to those terms I just introduced. Okay, first the context. So for a context, it includes four components. One is the OpenCL device, and the kernel, and the program object. Okay, so what is the program object? That's like the XCL bin. Okay, the bitstream file, the XCL bin is so-called program object. Yeah, and XCL bin inside we put together a lot of kernel functions. So we aggregate a lot of kernel functions into the program object. Yeah. Okay, and then we have a memory object. Yeah. So for a context, we have the actual FPGA device. We have a kernel. We have a program object and the memory object. Okay. For command queue, in the content for a command queue, you can have a kernel execution command. You can have a memory command. Memory command basically doing the memory transfer command. And you have a synchronization command. Yeah. So you can put those three items in the command queue. Okay, so context and command queue. Yeah. So let's look at the memory model. So for the OpenCL device, that they only work on the global memory. Okay, yeah. So the global memory is on the FPGA or the OpenCL device. That's inside the OpenCL device. Yeah. Or the board. Yeah, actually, it's, and then there's a constant memory. Yeah, and here in the OpenCL device, it may have the cache. Yeah. And each processing element work with is a private memory. Yeah, mostly the private memory is on-chip data buffers. And for each kernel function, you can think that's each kernel. There's a compute unit. Normally, it's yeah, that's normally what we say a kernel. And inside kernel, we may have a parallelism. So each one work with a work item. Okay, work item, that's the data set. Okay, for example, SIMD. Okay, so each data set, okay, is a work item, and there are multiple execution units, and the multiple execution units, that's a work group. Yeah. And so each work group, you have a local memory shared among different processing elements. Yeah. So in the memory hierarchy, you have a global memory, and you have a local memory, which shared by multiple, is local to the kernel or computing unit. And inside computing unit, you have a multiple processing element, and each work on its private memory. Yeah. So this memory hierarchy, yeah, it's important. Yeah. Okay. So this OpenCL the class that here basically link together all the context and command we just introduced. So for a context, that include a device and program, kernel, and memory object. Okay, so this is the context, and this is the command queue, and the whole thing together is a platform. Yeah, and here they talk about the relationship. So for each program, actually it has a multiple kernels. Okay, the star means a multiple. One program can have a multiple kernels. And for each device, FPGA device to have a multiple program or and each program may run multiple devices. Okay, so yeah, we can load program in multiple devices. Yeah, and for context, it can have a one context may have also multiple commands. Yeah. Okay, so in this diagram, introduce the relationship between the components in the OpenCL class. Yeah. Okay, so let's talk about XRT. XRT basically it has the following functions. Yeah, it does the image download and doing all the memory management. Yeah, it try to manage the multi-thread and process and allocate memory buffer and also keep track the buffer count. So it has to keep track of the usage of each buffer because it has to know the status of each buffer and see whether all the buffer has been used and then generate appropriate event or status to synchronize or manage multiple kernel execution or multiple process. Yeah. So it is the execution management. Okay. So you can manage the task queues, especially you can do the out of order execution up to 128 command slot. So for each command, you can think it's a command queue. It has a total 128 command slot. Yeah. So that means at one time you can have a 128 command outstanding, put into a queue, wait for execution. When it's executed, it's very much like a out of order processor. Yeah. So for each command, for each command it has a dependency relationship. Depend on what? Depend on the buffer available, or depend on previous command complete. So you can define the dependency, and later we will introduce how do you define the dependency using the event list, like to define the relationship of each command and buffers. So so it needs to monitor each kernel function execution status it also need to keep track each buffer status. Okay, so when for example, for this command, it depends on certain buffer availability or certain command being executed. And then the status is check if it satisfy all the buffer and command is ready, then you can execute this command. Yeah. So the command is not necessary to execute in order. All depends on the availability of its resources. Once the resource is available, it can execute. And so the XRT does all the management or scheduling about that. This is a very important features. Because we all know out of order make the utilization or the efficiency much improved. Yeah. And sometimes this thing is very interesting. Okay, the hardware scheduler. You know, the XRT running on the host, and you have a kernel function. Okay, all the kernel status is in the FPGA device, and all the buffer usage, everything happen in the FPGA device. XRT actually running here. So how does XRT keep track all this status from the remote device? It takes a lot of latency and overhead to communicate all those status. So itself introduce latency. All the status reflect in XRT. It takes latency to reflect the status. Takes some time. So if the status coming back late, that means you schedule the event also late. So it's easy to create the gap, the idle time. Yeah. So that's why that Xilinx introduced put the microblade MCU inside the FPGA, so that all the execution management can be offloaded to the local MCU. So part of the XRT function actually running in the local MCU. All the status is essentially is local inside the same chip. So the latency much reduced. So it can does much efficient scheduling. Yeah, I think you can understand why it's a benefit to put the MCU. And the MCU is very small. Okay, and then XRT also does the board management. Yeah. Okay. Hopefully, you have a rough idea what the XRT is doing. Yeah, especially the hardware scheduler. Yeah. So when we design my device, I also use a local MCU to do this scheduling. Yeah, instead of relying on a remote host. Okay, so the next I will take you through the Lab3 code. Yeah. Okay, so this is Lab3. Okay, we don't care the kernel function because what's talk of in this lab, what we like to give you is the whole framework for application acceleration. Yeah, we don't really care what it does in each kernel function. So in Lab3, we have 5 kernel functions. Okay, these 5 kernel functions, and we have multiple buffers. Okay, the buffer data in 1, data in 2, and data in 3 is originally located in the host memory, and then moved to the FPGA global memory. Yeah, and the buffer KA, KPB, KB, and the result that's those buffer is generated in the FPGA global memory. Yeah, And the result buffer, originally the content is filled in by the FPGA device, and the data will move back to the host memory. Yeah. And in this lab, we also run the command queue for out of order operations. Yeah. Okay. So basically, it gives you all the possible buffer usage. Yeah, and the data movement. Yeah, and the host program to manage all the data buffer is a very typical used in many of others application accelerator. Yeah, so the source code of Lab3 is a very good template for you to develop future application accelerators. Okay, so for the host code, basically there are three parts. First, you try to set out the hardware. Okay, next execute the kernel. After kernel is done, then we do the post processing and clean up. Okay, and so we will go through each step. For set up the hardware, first you need uh, to retrieve the platform and device and see what is available in the systems. Yeah, and then you create context. Yeah, we all know what context means. Yeah, and then we have a program the FPGA and create kernel object. Yeah. Okay, so basically you set up the context, identify the device and set up the context. And next step, you want to you start executing the kernel. To start executing the kernel, you need to allocate the buffer and move the data from host memory to FPGA, and you need to set up the kernel argument. And then you execute the kernel, and then wait for the kernel complete. That will be each kernel complete. There is in this lab you have 5 kernels. They interact with each other. So kernel and kernel, there's a synchronization between kernels, and we will see how the kernel synchronize with each other. So after the kernel execute and get the result data buffers, then host transfer the data to the host memory, then start the post-processing part. So we look at each step in the following slide. Okay, for set up the hardware, okay, those are the steps. Let's look at the detailed code here. Okay. So first, we need to identify the platform in the system. We try to get the platform information. Yeah. And in here, that's a platform object, and then it will return how many platform is found. And then we go into each platforms. And in this part, we need to make sure the platform is a Xilinx platform. Okay, this kernel function we develop the XCL bin we develop is on FPGA device, Xilinx FPGA device. So we have to make sure the XCL bin has to be running on the Xilinx devices. So that's what this code does. Yeah, to make sure the platform is a Xilinx platform. Okay. And then we identify, okay, the system does have Xilinx devices. Then we try to find the devices in this system with the given Xilinx platform. So this is the OpenCL code you are using the CL get device ID. Yeah, you give the target platform ID, which is Xilinx, and then you try to search the system for all the search for all of the FPGA devices, and then return all of the how many it returns how many FPGA devices it found with the Xilinx, which is a Xilinx device, and then it create the device objects. Yeah, and next it has to query the device. Since in this example, the XCL bin was compiled for this Xilinx device. Okay, so you besides identify it is a Xilinx device, you have to identify a specific FPGA device, which it is its name. So you look through each devices and then make sure the device is your target device. Yeah, and this target device is an argument that pass into the main function. Okay, so right now you have found the right Xilinx devices, which the original XCL being compiled for. Wait, what's happening? Not swipe through. Interesting. Oh, okay. Okay. Right now we identify this is the right device we're going to work on. Then next step, we will create a context. We'll create a context. Okay. Yeah. Okay. So this is a context we create. Yeah. Okay. And the context, it has a few components. Okay. You have and then we create a command queue. Okay. Using this command. Okay, the command queue in here, we need to pay attention to this argument. Right now, in this example, is 0, means it's in order command queue. Okay. The command queue is used between, it's established the communication between the host and target platforms. Yeah, and there are 3 types of a command queue. As we talk about, is kernel execution commands, the memory command, and synchronization commands. Yeah, and later on we will see how the command queue used for the kernel execution and the memory command. Okay, so the create command queue, this argument 0 means in order operation. And if out of order, you use this macro, yeah, to enable the out of order operation. Okay, and next we create a program, a kernel function. Okay, the whole kernel is compiled into a SCL file. So you basically load the file into a system memory. Okay, and then you create a program object. You create a program object. Yeah, and the program object is from this file image data in the system memory. Okay, so and then we extract each kernel from the program. Yeah, we have remember we have 5 kernel in the programs. So we will create kernels. Yeah, and give it the kernel name. And this kernel name is exactly the name as the function name in your HLS code. Okay, so then right now you have a kernel. Yeah. Okay. So you create each kernel here. Yeah. Okay, then next step, we will prepare to execute the kernel. Yeah. So what we need to do is first we need to allocate buffer in the host memory, and then we have to create corresponding buffers in the global memory. Yeah. In this example, we have a 3 host memory buffer, and we have how many? 1, 2, 3, 4, 5, 6, 7. We have a 7 buffer in the global memory. So in here, we create 3 host uh, buffers, and we create 7 buffer in the global memory. And then we are setting up the kernel argument. And then next, we do the data transfer. So as we just talked about, all the kernel functions operate on the global memory. So we have to move the data from host memory to global memory before we can execute the kernel. Yeah. And at the end, we synchronize the event. Yeah. Then let's look into the detail of each step. Okay. So we will create the host memory buffers. Actually, 4 buffer, the result buffer also we need to allocate. And in here, pay attention to we use this API that ensure the data is 4K aligned. Yeah. 4K alignment provide much more efficient for data movement. Yeah. So use this API to create the memory buffers. And then you generate the input data. Yeah, this function code. Yeah, and the result buffer you also allocate. Yeah. And next step, we create the global memory in the FPGA. Yeah, in here we have 7 global memory buffer in global memory, and you for the buffer in global memory, you have to identify its attribute. Remember the data 1, 2, 3. Actually, the data is from the host memory. Okay, you identify the attribute, the buffer. Actually, the data is from the host memory, and in the global memory, it can be read-write. For example, data in 1 buffer actually is read from the host memory, also written by the KV constant add. So that's why its rewrite attribute is read and write. And for the data in 2 and 3, it's read only. Okay, it's not written to by the kernel functions. And the other buffers actually only local to the global memory. Yeah, and each of the buffer is a rewrite, attribute is a rewrite. Yeah. Okay, and then result buffer is write only for the kernel, and we also share with the host memory data buffers. Yeah. Okay, so here, right now you know the attribute and usage for each data buffer. Okay, and the next step is set up the kernel argument. Okay, the kernel argument, let's take these KA functions. Okay, so what's the argument for this kernel function? It's identified by define like A and B, these 2 buffer. Okay, and then you need to have the buffer address. Yeah, and it's defined by the AXI light. Okay, the pole A has a corresponding AXI light. Basically, the host program will program the argument, the A buffer a buffer address, the buffer base address, and its size. The information is you have to program that so that he knows where to get the data from the global memory buffer. Yeah, the same as the result buffer. Oh. Okay, so for KA, you have two arguments you have to feed in. Okay, so for the A input is from the data buffer in one. Okay, this actually gives you the address of the buffers, and you program into this kernel function through the AXI Lite interface. Yeah, this is a very similar like a pink the Lab2 example. Yeah, and the result buffer. Yeah, also specify the buffer address here. So same thing for other kernel functions. Okay, so after you set up the kernel argument, and the next step we will do the data transfer to global memory. We have three data need to be transferred: data in 1, 2, 3 to its corresponding global memory buffers, and we use this command enqueue migrate memory object. Okay, and before people use the enqueue write buffers, but enqueue write buffer is no it's still there, but it's mostly deprecate. It's obsolete. So we supposed to use the enqueue migrate memory object, and this API provide few advantage. First thing is you can specify the memory object migration before dependent command. So that means that you can think of that we will specify all the dependency there and let the XRT to actually doing the buffer data buffer movement. Depends on the XRT will depends on the resource availability and other synchronization event, and automatically to execute that. And remember, when we write those programs, we write it's a static, and during the runtime there's all the status change, and there also has many of the synchronization event happen at the same time. So those behavior could not be captured when we write the code. Yeah. So this code, when we write those code, basically we simply set up execution control flow or control graph or data control graph, or yeah, specify all the dependency. Yeah. So this command queue only simply set out all the dependency graph here. And the actual running, the XRT will based on runtime status and event happens and execute dynamically at the runtime. Yeah. So this gives you a much more efficient utilization. Okay. So for data buffers, you can actually it gives you an flexibility that you can specify multiple buffer transfer in one command. In here, for example, we have 3 data buffers. We put the pointer into an array so that we specify, say we want to transfer 3 buffers, and starting from the memory buffer pointer 1, yeah, then there are continue 3 entries, specify 3 buffers, and use one command. Yeah. It's just a simple way to do the multiple data buffer transfer. Okay, for out of order execution, we have to pay attention to the Lab3 arguments for this API CL-NTU migrate memory object. For this argument, it specifies how many number of events in the wait list, and this argument is the event wait list. And the last argument is the event is generated. So it depends on these events, and after it finish, it generate the last event here. Okay, let's take an example here. Yeah. In this example, the command queue was created with the argument 0 here. That means it's in order. Okay, so if it's in order, then the XRT simply execute the command as you specify here. So it will first doing the buffer A movement. Okay, the command queue here is yeah, do the buffer A move. The next one is the buffer B move. And then in sequence, you execute kernel A. The CL-NTU task means that you execute the kernel function, trigger the kernel function to execute. Yeah. So you will execute KA, KB, KX, and K result in sequence. Yeah. And when the result done, then you do the result buffer. You move the data from global memory to host memory. Yeah, and then you finish. Yeah. So if it's in order command queue, so you don't specify any of the event list or event generation. Yeah, so it's null here. And this example is the out of execution, and this is the dependency graph. Okay, so let's look at the code in detail. Okay, first you create the command queue with this argument. So this means it's out of order. Okay, and then here, look at here. So for the buffer A movement, it doesn't depend on any event, and it will generate event 1 here. And for the transfer the buffer B, it doesn't depend on any prior event. After it finishes, it generates event 2. And we see KA, in order to execute the kernel KA, the buffer, data buffer A must be ready. So if we want to execute KA, it depends on one event, which the E1 event, and it will generate E3 event. So for KB kernel, it depends on the buffer B, which is the event 2 here. It will generate, after the kernel execute, then it will generate the event 4. To execute KX, you must have a KA and KB complete. So it depends on 2 events. There will be 2 events and event 3. So there will be 2 starting from event 3. So the next one is the entry 4, so which is the event 4. Yeah. So in here, you try to use this way to specify multiple event dependency. So you have to make sure they are put into a consecutive entry of this array, event array. Okay, and then the result, kernel K result depend on the KX complete. So they depend on the event 5 and generate event 6. Yeah. So we use the Lab3 argument to specify all the data buffer and kernel execution dependency using the event list. That's the way doing the out-level execution. Okay, so okay, and in this example, you can also use this barrier with a wait list. Okay, so this command basically set a fence. You can think that's also barrier, or you can say it's a fence. So this thing will complete before after all of the prior command or buffer all completed. That means all the command queue has to be empty. Yeah, before it proceed. Yeah, so you put a barrier here. It saves. Yeah, sometimes yeah, you just make sure everything has to. That's a basic synchronization point. Everything before that has to be completed before it can proceed. Okay, let's take this our real lab 3 example. Okay, that's the execution graph we have. Yeah. So in here we will see for this kernel function, it doesn't depend anything. We generate event 0. So for KA to SQ, you have to make sure KV constant kernel complete. So for KA to complete, you have to make sure this event is ready, which is the KV constant add kernel function complete. And you generate event 2. So for KPB to SQ, it doesn't depend on anything. After it finishes, it generate event 1. And KB depend on the event 1 and generate the event 3. So to SQ the K calculate, it depends on KA, KB complete. Okay, so which is event 2 and 3. 2 is the KA and 3 is the KB. Yeah. So after finish, you generate event 4. Okay, so the time you can move the result buffer to host program, you have to wait for the K calculate kernel complete, which is the event 4. So before you can move the data buffer back, it depends on the event 4 complete. Yeah. So this is our the Lab3 code. Okay. Okay. So after complete, we just post process and clean it up. Yeah. Basically, you try to release all the memory objects, release all the kernels, and program all these things. Yeah. Okay. So this is the result. So when you run the Lab3, you can compare the system performance by running the Vitis analyzer. Yeah. And Vitis tool provide a lot of analysis tools, and the timeline is one very useful utilities, and we can observe the timing event happens. Yeah. And in this one, it's in order operations. So we will see each kernel function SQ in sequence. Yeah. And the next timeline is for out of order. So we can see KA and KB actually running in parallel. and the calculate must can only execute after KA and KB complete. So it does show the follow the dependency we specify in our code. Yeah. So after you execute, then you can also run the analyze the profile summary. Yeah, it shows all the kernel execution and memory rewrite the time. Yeah, from here you can observe the how much time it takes to transfer the data and to execute the kernel. Yeah. So from that, you can know how I can pipeline or rearrange the sequence of the kernel execution in order to compact or increase the utilization, either on the data bus transfer or the FPGA kernel execution. Yeah. So for example, if a certain kernel function takes too long of time, then maybe we can put two parallel shorter kernel function in parallel with the longer kernel function execution. Yeah. So by observing of this, we know how to arrange or schedule the data transfer and kernel function so that it maximize the PCIe bus transfer or optimize the kernel function execution to minimize its idle times. Yeah. So those information is very important because by looking at the code, we really don't have an idea how much time it takes to execute or transfer data. Yeah. With this, we have an actual duration. Yeah. It will give us much better control. Yeah, in doing the scheduling. And the scheduling also, yeah, that's how we write our code. Yeah. Then we can in some way to control the way the XRT schedule is kernel execution. Okay, yeah. So this at this point, yeah, I go through the Lab3 codes. Yeah, hopefully give you an idea that how the Lab3 is functional. Yeah. Is there any questions?
Yes. Hello.
Yes.
Professor Lai, I'm wondering, does it mean that we can have multiple overlay instance running simultaneously on a FPGA?
Oh yes, yeah. In FPGA, actually we can have multiple. Wait, let me go back. Remember here. Yeah. So remember here, for each kernel, each FPGA device. Let's play here. For each FPGA device, look at here. This is one FPGA device. We have a multiple execution unit. So we have a multiple kernel. Okay, so we can have a multiple kernel running at the same time. So suppose we have a kernel function developed and it doesn't take much resource. So actually we can instantiate multiple kernel, even though they are same kernel. Yeah, we can instantiate multiple kernel running at the same time in one FPGA device, as long as it feeds into the FPGA resources. Yeah.
Okay, thank you.
Mm-hmm. Yeah. Even though, yeah, recently I advised a team to do image processing kernel, and I advised him using the SIMD. Yeah. In later lecture, I will introduce a vector data type. Yeah. So the vector data type For example, you can have when you write the code, kernel function, you can write in a way that's configurable. For example, for the kernel function, all of the interface, if the interface we declare as a vector, and the data type is integer, and you can specify n here. N is a macro. That means you can have n duplicate of integers. Okay, so if you write your kernel function in this way, then we can, when we compile our kernel function, we can specify the n, and depends on how much resource used in the FPGA. Yeah, we adjust different n and see the resource usage, and then we choose a different n value to provide different parallelism. Yeah. So when we write the AAHLS code, we want to write in a way that leverage on C++ syntax, so that make the kernel is more programmable, parameterized. Yeah. Okay. So you can think of the n just like a number of PE here. Yeah. And the PE can be, yeah, just a Markov definition, so it can easy to change. Yeah. We should write a kernel in this way. Yeah. So that the kernel is much more flexible, useful. Okay, Yilin, right? Yes.
Yes, good evening, Professor Lai. And I just wonder if there are so many programs that is run in parallel, and the FPGA cannot accommodate such programs because the FPGA doesn't have so many resources. And who is responsible for the resources allocation, and how does it allocate the resources? Thank you.
Oh, you were saying if the FPGA resource is not enough, right?
Yeah, exactly.
Okay. And then you can always use pragma. This thing we haven't teach because we haven't really touched the core of the HLS coding. Yeah, you can in HLS they provide pragma to control the parallelism. For example, for a loop. Okay, and then you can enroll to provide a lot of parallelism, or you can use a row, and the resource will much reduce. Yeah, and you can also enroll with factor to provide different level of parallelisms. Yeah. So to answer your question, that you use the HLS pragma to control parallelism and resource allocation. And that's the one thing using pragma. And pragma, for example, you can do the sharing. For example, I have a lot of operation. We have an expression. Yeah. In this expression, we use multiple multiplier or adders, for example. Okay. We can also use pragma using the pragma resource. We can limit it. We can limit the multiplier equal 1. We're just using one multiplier. Okay, and the synthesis tool will try to do the resource sharing and to schedule in different cycles and generate all the control logic and use single multiplier. However, it will take longer latency. Yeah. Yeah. So HLS provide this pragma, give you a very handy way to control the resource usage and balance with the parallelism. Yeah, that's how you do it.
May I follow up?
Yes.
Okay, so suppose that we have the program that we schedule a program like such amount of the program can be run in parallel, but we may put the program on different FPGA, and each FPGA has a different amount of resources. So can I set the pragma such that if the FPGA has resources that I want to run this loads of this program in parallel, and if not, I want to run some of the program in these program first, and then run the other one.
Can you repeat the question again? Yeah.
Okay.
So you are talking about you want to develop the AAHLS code so that it can be used for different capacity of different FPGA with different capacity, right? And with one single AAHLS code.
Yes.
Right. Okay. Yeah. That's our purpose to teach the AAHLS. I want everybody can write the code with this flexibility. Yeah. Without really touch the core of AAHLS source code. Okay. So there are two ways to do that. Okay. First is the data type. Like I was just saying that if you use the data type of vectors, okay, and then the Markov n decide number of PE. Okay, so that you can have a same source code without touching the source code. You simply redefine the Markov n. Then it give you different parallelism and different resource usage. So that's a data type, okay? And the for loop, as I say, the enroll, okay? So how much parallelism you want to enroll, you can specify the vector n. Again, that you don't touch your source code. You change your Markov definition file. It give you different enroll parallelism. Okay. Again, like a resource, pragma resource. Okay, I can say how many multiplier I want. Yeah, again, you can say it's a Markov n. Then you specify how many multiplier I want. Yeah.
I see. Thank you.
And then without touching touching your source code. That's the best. You don't want to say, oh, I want bigger device, and then I have to go into the source code to change it. Yeah. That's that will create a lot of unexpected mistake. Yeah. Okay. So simply you trust the tool will do the right thing for you. You don't need to verify whether the tool is function correctly. Yeah, you have to trust the tool do the things it says correctly. Yeah, without break your function. Yeah. Okay. Yeah, so that's what we want to learn in this course. Yeah, write a very neat AAHLS code that's flexible and expandable. Okay. Any more questions?
Oh yes. I want to ask one more question. If we allow several overlay on FPGA run simultaneously, does it mean that when we load an overlay, then the FPGA need to decide the topology on the fly? That is, does it mean FPGA need to decide the routing and placement when we load the overlay? Because according to my understanding, we already decided the routing and placement during Vivado synthesis. But when we allow multiple overlay, then we need to route and place them when we load them. So yeah.
Okay. Yeah. So because I haven't talked about the FPGA architecture, so you may not have a correct idea about how FPGA functions. Yeah. Remember, FPGA, the functionality, you are talking about placement route. Okay. So the concept placement route is from the IC design. Okay. So you place and route, then you go to the fab, then it deposits the metals and create the device. Okay, but in FPGA, all the functionality, even though when you say place and route, basically is a different wiring, the different wiring patterns. The wiring pattern itself is programmable. It's a SRAM control. So when you reconfigure the FPGA function, you just load in different bitstream file. Then it performs different function. Okay, so in FPGA, like Xilinx FPGA, I don't know Altera. Maybe they have the same thing. They have a so-called partial programming. Let me maybe draw one thing. How do I draw? I want to insert a slide. Okay. Okay, let me show a slide. Okay, in FPGA, okay, for example, this FPGA is a PCIe device. Okay, so you have a PCIe transceiver, and you have a PCIe IP to communicate with the host. Okay, and the FPGA you can specify a region. That region is a so-called partial programming region. Okay, so there are certain part of FPGA is static. That means they are fixed function. They has to be always there. For example, to communicate with host, this part of logic you cannot change. Once you change it, you disconnect from the host. Okay. However, certain part of FPGA can be reload. Okay. So the same FPGA during the runtime, you can load different bitstream file within this for this region. Okay, so imagine that I have a FPGA. Okay, I partition for these two regions. Okay, so when I execute a kernel function running in this region, and when you run in this region, I can update the other region. When you run in this region, I update this region. So that you virtually increase the FPGA capacity. Yeah. So to update this FPGA, maybe spend a few milliseconds. As long as the latency of this execution is longer than the millisecond. So when you switch the two, you almost see transparent, yeah, without wasting any time. Yeah.
Okay, thank you.
Yeah. Okay. So that's a partial programming. Yeah. Okay. Any more question? Okay. So let's move on to next topic.